Hey everyone, and welcome back to the channel. Today, we're tackling LeetCode problem number 10, regular expression matching. This is a classic problem, often seen in coding interviews, and it's categorized as medium difficulty. The goal is to implement a function that takes two strings as input, a text string and a regular expression pattern. We need to determine if the text string matches the given regular expression pattern. The pattern can contain dot, which matches any single character, and star, which means 0 or more occurrences of the preceding character. So it's not your simple string comparison. It involves understanding the nuances of regular expressions. We'll be focusing on a dynamic programming solution, which is an elegant and efficient approach to this problem. Get ready to dive in. It's going to be a fun challenge. Understanding with examples. Let's clarify with some examples. If the text is AA and the pattern is A, it doesn't match because the pattern only has one A. But if the pattern is AA, it's a perfect match. Now consider the pattern A star. The star means 0 or more A's, so it matches both empty string A, AA, AAA, and so on. Let's look at a more complex example. Text equals AAB and pattern equals C star A star B. The C star means 0 or more C's, so it essentially disappears. Then we have A star, which matches the two A's in the text, and finally B matches the B at the end. So this is a match. Let's try another one. Text equals Mississippi and pattern equals Miss star is P star. This one is a bit trickier, but we'll break it down step by step using our dynamic programming solution. Understanding these examples is crucial before we jump into the algorithm. Brute force approach. A naive approach might be to try all possible combinations, essentially brute forcing our way through. We could recursively check for matches, trying out all possible interpretations of the star characters. However, this quickly becomes computationally expensive. Imagine the number of combinations exploding with longer strings and more complex patterns. The time complexity of this brute force method would be exponential, making it completely impractical for even moderately sized inputs. This highlights the need for a more efficient strategy, which is where dynamic programming comes in. Optimal solution. Our optimal solution uses dynamic programming to avoid redundant computations. We'll create a table, a 2D array, where each cell represents whether a substring of the text matches a prefix of the pattern. The table's rows correspond to the text string and columns correspond to the pattern. We'll build this table bottom up, starting with the base cases. For example, if either the text substring or the pattern prefix is empty, the match depends on the presence of star in the pattern. Then we'll iterate through the table, making decisions based on whether the current characters match or if a star character necessitates considering multiple possibilities. This dynamic programming approach allows us to efficiently reuse previously computed results, dramatically reducing the time complexity. Code implementation. Let's see the code in Python. We'll first initialize our dynamic programming table. Then we will handle base cases and iteratively fill out the table. The core logic relies on checking character matches and interpreting the star wildcard character. We'll carefully walk through each step and explain the code line by line. We'll handle the edge cases and optimize the code for readability and efficiency. Remember that understanding the dynamic programming table is key to grasping the entire solution. The code might look complex initially, but by carefully following the execution and comments, you'll see how elegantly it solves the problem. Time and space complexity. Our dynamic programming solution boasts a significant improvement over the brute force method. The time complexity is O of m times n, where m is the length of the text and n is the length of the pattern. This is because we're filling an m by n table. The space complexity is also O of m times n, since we're using a 2D array to store our results. While this is better than exponential time, it's still worth noting that the space usage might become an issue for extremely long inputs. There are some space optimization techniques we could explore, like reducing the table to a 1D array. I'll leave that as an exercise for you to think about and improve upon. But what we've accomplished is already a considerable improvement over the original exponential time complexity. Engagement break. So, what did you think of that explanation? Did you find the dynamic programming approach helpful? If you found this video useful, please give it a thumbs up. It really helps the channel grow. And if you want to see more LeetCode solutions and algorithm tutorials, be sure to hit that subscribe button and ring the notification bell so you don't miss out on future videos. Leave a comment below with your thoughts, suggestions, or any questions you might have. Let's keep this community thriving with knowledge and discussion. Conclusion. In this video, we've successfully tackled the regular expression matching problem on LeetCode using dynamic programming. We started with a clear understanding of the problem, explored a naive approach, and then moved on to an efficient solution.